Alright, so question about the cosine rule here. How did we go about proving that? We did see it in class, but I know you're going to need to see this more than once, so let's do it again. Let me first find a little triangle that I made before. There we go. Now what have I got here? I've just got an ABC triangle, so it could be any triangle. And because this looks like it's got a bit of Pythagoras' theorem in it, look at all those squares there, I've created a right angle triangle, and in fact I've created two, haven't I? By dropping that altitude there, I've now got the yellow triangle on the left and the blue one on the right. Let's have a look what happens if I write Pythagoras' theorem for these triangles. Now note, this entire base was called B, wasn't it? But the problem there is, in the yellow triangle it's not a full part of B, and in the blue triangle it's not a full section of B. So all I've done, labelled this part of it here X, the bit on the right for the blue triangle, so the bit on the left would be the entire distance minus that bit on the right, so B minus X. Let's go ahead and write Pythagoras' theorem and see where it gets us. For the yellow triangle, the hypotenuse is C, so the square on the hypotenuse, C squared, equals the sum of the squares on the other two sides. That's B minus X all squared plus H squared. For the second triangle, the hypotenuse is A, so the square on the hypotenuse, A squared, equals the sum of the squares on the other two sides. Beautiful. Now I went to the trouble of colour coding them before I stuck them in, so let's actually use that to our advantage and just make it a little bit easier so you can see where those rules came from. Now, problems. I've got H's and I've got X's, and H's and X's, neither of them appear in my cosine rule. Well, let's deal with one of them first, then we'll deal with the other one. Now, I think I want to get rid of the H's first. They seem a little bit easier to have those things equal to each other. You could get rid of the X's, it doesn't really matter. But I've decided H's, so that's what I'm going to do. Now, this one looks like the easier one to rearrange, so why don't we just do that one? So over here, to get H squared on its own, I need to subtract X squared. So A squared minus X squared equals H squared. Okay, that I can work with. Let's sub that in to the first equation. So I'm going to substitute A squared minus X squared for H squared in equation 1. What has equation 1 become? Well, it's now going to be C squared equals B minus X all squared plus A squared minus X squared. That's the expression I'm going to have instead of H squared, because we know that they're equal to each other. Okay, let's expand this bracket, because that negative H squared, I can see I'm going to get a positive H squared out of there. Let's see what that's equivalent to. C squared equals B squared minus 2BX plus X squared plus A squared minus X squared. Hopefully you all followed that. Some of you won't have, though, I know that. What did I do to get from B minus X all squared? Where has this negative 2BX come from? Let's just remind ourselves of our distributive law. When I have the square of a difference, it's the first term squared minus 2 times the first times the second plus the second term squared. Still not sure if you believe me or not. I don't want to give it away. We've been doing this for 3 years at least now. You go back and you try foil or crab claw or smiley face. Remember crab claw? That's my sort of favourite. Oh, that's a bad. That looks like I'm going to draw a smiley face. Oh, well, there's smiley face. There you go. That's one way you can do it. That's getting a bit messy now. Get this eraser out. So remember, foil just first, outer, inner, last. And I've rubbed out too much now. All that little effort trying to make things clearer for you, and I probably made it clear as mud. Crab claw, of course, is where the first one multiplies everything in the second bracket, and then the second one. And you can see that makes like a nice little sharp pincer or crab claw there. But really, what is it? It's the distributive law. That's all you need to remember it as. If you remember your distributive law, your maths and your life will be easy. or at least easier. Enough of that. We've digressed. Let's get back. What can you see over here on the left-hand side? You've probably been saying, hurry up and get to it. Look at that. Plus x squared minus x squared. Cancel each other out, don't they? I nearly have the perfect expression for the cosine rule. I've got c squared equals a squared plus b squared minus 2bx. That looks almost the same, except this c cos a is there instead of x. Can we deal with that? I think we can. Some of you are saying, but hang on, sir. This is c squared. Your other one says a squared in the cosine rule. But remember, when we label these things, it's totally arbitrary which one we called a, b, and c. I could just as easily write this rule as b squared equals a squared plus c squared minus 2ac cosine of b. Or c squared equals a squared plus b squared minus 2ab cosine of c. It really doesn't matter, does it? You can see I could just go ahead and change the labels, put a there, b there, and c there, and I'd have little a over here, little b up there, little c there, and it would still work the same way. So the letters are a little bit arbitrary. What's important is that we've shown that it works for any generic value. All right, what am I going to do about this x? Well, we know the x requires a cosine to get rid of the x. That's what we want to have in our rule. So x would be the adjacent side in that blue triangle. So from that blue triangle, what rule could I write? So here's a little thing from the blue triangle. And here's a nice little way. You could just call it triangle 1 or triangle 2, or you could label the sides. There we go. From the blue triangle, the cosine of c equals the adjacent divided by the hypotenuse is a. If I multiply through by a, I get a cosine c equals x. And I'm going to make that substitution. So we say substitute a cosine c for x. Therefore, c squared equals a squared plus b squared minus 2b, and I replace x with a cosine c. And there we have the same expression. Look, I've got AB there and BA down here. It's nicer if you write it with A and then B. So let's put it in beautiful alphabetical order just to keep everyone happy. And that is a proof that for any triangle, the square on one side equals the sum of the squares on the other sides minus 2 times the two side lengths times the cosine of the angle in between them. Crazy that someone thought to even try and do that way back when, but not so hard for us to do now. Have a look over it, try it again. Good luck with it. It's probably not going to be examined, but it's really good if you can understand the process of proving something in maths, using generic values A, B, and C so they could represent anything, proving that it doesn't matter what they are, the rule follows. That's a fundamental thing we do in maths to try and come up with useful rules to apply in a whole bunch of situations. All right, enough from me. Catch you in the next one, guys. Bye.